Good evening, everybody. I'm Anil Anhati. Today I'm going to talk about some of our recent works on dimensionality effects on superconductivity in LA-2 nanostructures. So this work is done at University of Pittsburgh and Professor Jeremy Levy's lab. So as I shown in the cartoon, so in this study we made nanostructures by varying the width, ranging from 10 nanometers to a 1 micron width, and as I've shown here, what we have seen here is the enhancement in a critical current when the nanostructures have a width less than 100 nanometers. So a brief introduction to the LA-2 interface system. As most of the people in the room know, it has a very sharp metal insulator transition at about 3 unit cells, where when we grow LAO above 3 unit cells, the system becomes conducting at the interface. And the 3 unit cell LAO STO can be tunable by applying a backgate, which can be switched from insulating to conducting state and vice versa. So another important or interesting property at the interface is it has a tunable superconductivity at about 300 millikelvin, and which was also further shown to be gate tunable. The superconductivity was extensively investigated in recent years, for example here by Manhattan Group, where they have shown that the LA-2 interface has a similar a phase diagram similar to the high TC superconductors, where depending upon the charge carrier density, the TC shows a dome shape, and also it has a same gap behavior similar to the copper oxide systems. And recently from our group we investigated specific devices made up of these nanowires, which are the cavity devices, which have shown that electrons not only shows a Cooper pairing but also shows a electron pairing without superconductivity, depending on the carrier density and gate regime you are in, and also depending on the source and drain leads, you can form a bound states which are with the quasi-particle and Cooper pair combinations. So what happens to the superconductivity in low dimensions, right? So when the films, since the superconductivity at the LA-2 interface is 2D, for example, when the magnetic field is applied in plane and out of plane, what it has shown that the critical field shows an anisotropic behavior. This is a dimensionality effect already in the 2D. For example, imagine a case that we have a case now with thickness and both are comparable or less than the coherence length. So depending upon the width and your thickness, it defines how the flux enters into your system, right? So according to the Ginzburg-Landau theory, so the vortex, for example, when it enters into applied a magnetic field, only enters when the thickness is greater than 1.8 times the coherence length. So our objective is to not only the width, thickness, just reduce the width of the devices also, and see what happens in the lower dimensions and crossover regime. And we wanted to investigate critical current and critical field and TC dependence with respect to the width. So we use conducting AFM technique to create these nanostructures with variable width, and which is a well-developed technique in Professor Jeremy's lab. And we use a 3.5 unit cell insulating LA-2 interface, and by applying a positive voltage onto the AFM tip, we can make the interface conducting. And Patrick et al. Have made devices with a variable width in the past, and in these devices, when the devices are made with the width of 100 nanometer or less, what we also saw the enhanced mobility. So these nanostructures show a cleaner transport and with the enhanced mobility, and we have also saw the superconductivity in these nanostructures. So this is a sort of common patterning technique that we follow Basically what we have shown here is that we make the goal connected interface connections first, and then we use AFM tip to write a device sketch on the given canvas. So in this study we made nanostructures with basically we define like a nanowire which is having of 10 to 20 nanometers width, and a structure of 100 nanometers and a 1 micron structure, and all of them have a 3 micrometer length to compare the properties better. So this is the schematic how the AFM tip creates and structures. First it writes a nanowire, and then a 100 nanometer section, and then a 1 micron section. Yeah. So here first we measure IV curves of these 3 structures, and what we do is, since we measure all of the devices simultaneously, because whenever we apply gate or temperature we don't want to have a deviations, and we measure all of them together with the 6 leads what we have shown here. So what you see in IV curves that for a nanowire and 100 nanometer section, which is shown in red and blue color, so they show a larger normal state normal state resistance, but whereas 1 micron section has a smaller normal state resistance, which you expect from the dimensionality perspective. But whereas in the superconducting state, it shows that the supercurrent doesn't vary much, it deviates from the dimensionality, right? Generally you expect a dimensionality scaling with the critical current also, but it appears that it deviates. So we measure the temperature dependent by varying the temperature from up to 500 millikelvin, from 50 millikelvin, and we scan the critical current. And what we see here, what you see here is the third axis is a resistance here. Basically the critical current appears to be in between 10 to 15 nanoamps, and it is larger for 1 micron section, but it's not definitely not scaling with the dimensionality. And below what you see here is a differential resistance which is obtained at near zero current bias, and what you see is a clear superconducting transition in all the 3 sections. Of course, if you look at carefully, that superconducting critical temperature is lower for 1 micron section, and also it has a finite resistance state even in the superconducting state. But interestingly, nanowires and 100 nanometers, we could see almost a zero state resistance in the superconducting state. So we further did gate tuning, because the critical current or the normal state what you see depends on the gate voltage. So we wanted to scan the entire range, accessible range, so that to map the properties in the whole gate range. So what I've shown here is a critical current density, which I obtained by dividing with the width of the structures, and normal state resistance, which is sort of resistivity. So what we see there when we do a scaling, critical current density is larger for nanowires and 100 nanometer section compared to the 1 micron, and we have reproduced these results in 3 devices. In all the 3 devices, nanowire always shows a higher critical current density, and there appears a dependence of the gate voltage, but at no point it scales with the dimensionality appears. Whereas in the normal state, if you can see, when we normalized resistance with respect to the width, and what we see is a nice scaling for the 100 nanometer and 1 micron section, which rules out that disorder, for example, is not the case for what we see in the superconductivity, right? If you have a disorder or something, you never expect the dimensionality to scale down. But however, we have a lower resistivity, which in the nanowire section, which we believe that due to the high mobility that also seen in the past. So here I compare various literatures and our data. So at least in a 1 micron section, in all of 3 devices, the values what we see for critical current density also scales with the references on the LAO STO, which are made on different widths and geometries, and we have a more or less same value. So we believe that in the bulks, like 1 micron section, it scales well and agrees well with the literature. However, when we see in the 100 nanometer or less sections, we see a clear enhancement in the critical current. So what we believe is possibly in the 100 nanometers and 1 nanowire sections, there is an additional contribution to the bulk superconductivity, which we believe originating from the edges. We don't know at this point that these are really edge states or not, but definitely the edge superconductivity seems to be different from the bulk. And to understand this, we fit to a model which takes a consideration into the two components to the critical current density. One is originates from the bulk and one is originates from the edges, which actually depends on your width and also your penetration depth into the material. Since for LAO-STO the penetration depths are about 3 micrometers, so we believe we are in the nanowire sections. They are very much smaller compared to the penetration depths here. So the formula fits well to the one of this data set with where we can fit nicely in the entire range. So which is reasonable to think that you have a 2 component to the superconductivity. And we further did a magnetic field dependence to see that what happens to the critical field for these sections. So if you look at the top nanowire, so these are different field dependence obtained at different gate values. Again, when you see at lower gate value -10 volts, for example, this is a sort of underdoped range, and you see a very small superconducting critical current. And when you reduce the gate value, which means that you are doping the system, and you can see an evolution of a critical field and saturate, and this again decreases towards a overdoped range, which is true for all the 3 cases, like nanowires, 100 nanometers, and 1 micron section. And we extract the critical fields from these at each gate value and plot it here. What we see thing is a clear difference between the nanostructures and the 1 micron section, where we see a larger critical magnetic field in nanowires and 100 nanometer sections, and which is about 0.4 to 0.5 Tesla, which are comparatively larger to the 1 micron section. And in the literature also for like conventional 2D systems, the out of plane critical field is about 0.2 Tesla. So we see a clear enhancement for nanostructure, which we believe again when the vortex entry into your system start playing right, because at some point of time you expect that vortex cannot enter or it becomes harder to enter into the system. And we extract further coherent length, in-plane coherent length for this different sections, and for the nanostructures it's always lower into the systems. Yeah, so to conclude my talk, and in this presentation I've shown that the dimensionality definitely affects the superconductivity in LAO-STO, and it all violating the dimensionality scaling, at least for a critical field and critical current. And we have shown a enhanced critical current for narrower channels, and we believe that this is coming from the edge contributions. And our magnetic field data suggests that there is an enhancement in a critical field for narrow channels, and it suggests that you can expect a novel vortex dynamics in the narrow channels. For example, we can realize a sort of a quantum phenomena which is called a Weber blockade. Imagine that at a certain point of time you just vortex start to enter. If we can count these vortexes, and it can be used for technical implications. Thank you.